Chapter 29, we're going to expand our knowledge of exponents, and we're going to talk about some rules for exponents. When you have several exponents, when you multiply things, when you take something that has an exponent and raise it to an additional exponent. And so far we haven't run into many situations where we actually manipulate the exponents. We know what an exponent is. It's simply just a shorthand way to write repeated multiplication. And we have a few instances of exponents listed here, A through E, that we've already dealt with. So we'll sort of recap what we know and how to apply exponents, and then we'll try to learn a few new tricks that we can use in terms of exponents. So first case, we have a 2 to the 5th power, and that simply means that we have 1, 2, 3, 4, 5 2's, and they're all multiplied times one another. Okay, so 2 times 2 is 4, times another 2 would give us an 8, times another 2 would give us a 16, and then 16 times 2 is 32. How do we deal with negative numbers that have exponents attached to them? Well, in this case, we look at this as the 3 having the exponent of 2, but the 2 does not apply to the negative sign. So we just carry the negative over to the right, and we square the 3. There's only 2 3's. Okay, there's not 2 negatives. The 2 doesn't apply to the negative. So we end up with a negative 9. In an alternate situation involving parentheses, in this case, the 2 applies to anything inside the parentheses. It's just outside, up above the parentheses. So this means that we have 2 of anything inside the parentheses multiplied. So we have a negative 3 times another negative 3. This would give us a positive 9. In this case, about all we can do with this expression, 4x to the 3rd, is write it as a 4 times x times x times x. And we typically call this expanding the exponent. The next one is a 4x to the 3rd, however we have parentheses, and the 4 is included inside the parentheses, and so we have 3 of these. So not only do we have 3 x's like the last example, we now have 3 4's, and 4 times 4 is 16, times another 4 would give us 40 plus, let's see, 24, 64. And we could write this as x to the 3rd because we have an x times x times x. 3x's multiplied, shorthand notation, x to the 3rd power. So that's sort of a summary of what we know about exponents. The only other situation where we've dealt with exponents is, for instance, if we have an expression like this, okay, several instances of the same variable but with different exponents, then what we know is that in order to combine like terms, we have to have the same variable and exponent, and so these are like terms, as well as these two terms are like. And that just simply means that we can add and subtract them, but when we do this, we do not change the exponents. So if I have one x squared term and then two x squared terms here, then I would simply rewrite this expression as a 3x squared, and then 1x minus 3x would give us a negative 2x. And at that point, we can't go any further. Okay, this expression has been simplified. We cannot combine an x squared with an x. The exponents have to be the same. So the first rule we're going to look at is called the product rule, and it's an instance where we have two variables or numbers. Each variable or number, okay, in this case they're the same. Each one has a different exponent. Here I have an x raised to the second power. Here I have an x to the fifth power, and they're actually being multiplied now. And so before, we may have seen something like this before, x squared plus an x to the fifth. We can't add these, the different exponents. But now we're changing the operation. We're multiplying these. And so one way you can look at this expression is to take each instance of exponent and expand it. Okay, write the expression without the exponent. So x squared is 2x's multiplied. X to the fifth is 1, 2, 3, 4, 5x's multiplied. And then so if we multiply these two together, we have 2x's times more multiplication times 5x's, 2x's times 5x's. Alright, so we just have a string of x's here. In other words, we have 1, 2, 3, 4, 5, 6, 7 x's, and all of this involves multiplication. What is 7 x's multiplied together? Well, we would apply an exponent. We can use exponents to describe repeated multiplication. This would be an x to the 7th. And so another way that we could simplify x squared times x to the fifth, instead of expanding it out and then counting the x's, is to just simply note that we can add the exponents. 2 plus 5 is 7. So the product rule stated in general, when the bases are the same, and that's very important, if the bases are the same, and the base in this case is an x, the base of this exponential expression is x, what we can do is simply add the exponents. And so that makes example 1 pretty easy. All we need to really do before we apply the product rule is to check the bases. If the bases are the same and we're multiplying the two expressions, then we simply add the exponents. So this would become a 2 to the 4 plus 6. We can condense this to 1t, and 4 plus 6 is a 10. So t to the 4 times t to the 6 is a t to the 10th power. This also applies to several instances of the same variable with different exponents, but they must be multiplied. So this is m squared times m to the third times m to the fourth. So if there's multiplication and the bases are the same, we can condense it to one instance of the variable and add up the exponents. 2 plus 3 is 5, plus 4 is 9. And so what you're going to see is we only manipulate the exponents whenever we're dealing with multiplication. And later you'll see that we also manipulate the exponents when we divide or if we're applying another exponent. Okay, so far product rule involves multiplication. X times x, well, there's no exponent written, so it's understood that each x has an exponent of 1. And so to simplify this, condense it into one x variable, we add 1 plus 1, and we get x squared. The same applies to numbers. We have two exponential expressions. One of them is 3 squared, the other one is 3 to the 5th, and they're multiplied, so we have the dot in between them, and the bases are the same, and so we would write 1 3 as our base, and then simply add the original two exponents, 2 plus 5, and so we get 3 to the 7th power. If we bring up our calculator and we calculate 3 squared times 3 to the 5th, we could write it this way, the way it was given in the workbook. We get a pretty big number, 2,187, and we can compare that to just a single 3 raised to the 7th power, and we get the same result, 2,187. So the expressions are equivalent. Okay, so what do we do if these expressions have coefficients? Okay, so we have bases, x, x, we have exponents, 3 and 9, and we have coefficients 2 and 5. Well, the order of multiplication doesn't matter. It's commutative. And so what we can do is just arrange everything according to their likeness. 2 and 5 are coefficients, so we can simply set them side by side. And then the x's are the exponential expressions. We put those side by side, x to the 3rd times x to the 9th. And so we kind of have two problems here. We multiply two real numbers, 2 times 5, and we get 10. And then we multiply two exponential expressions with the same base, x times x, and we add the exponents 3 and 9. So 3 plus 9 gives us 12. Alright, why can we arrange the factors in the product like this? Multiplication is commutative. So in example 2, we're really just doing more of what we learned on the previous page. We're applying the product rule. It's just now we've thrown in some different variables and some coefficients. For instance, a, we have a coefficient of 5 and 8, and there's two different variables, an m and an n. So we'll arrange everything the way we were shown in the example. We'll write the multiplication of the two coefficients first, and then whatever we get from that is multiplied times our m's, and then we write our n, and there's only one. So as far as what we can do with this product, we can multiply the coefficients and get 40, and we can multiply the m's and get an m to the 7 plus 1. With this single m and no exponent, it's understood that it has the exponent of 1. So m to the 7 plus 1. And then we're left with a single n, and we can't mix this with any of the other components of the expression. It's just simply by itself. And so this final expression is as much as we can simplify it. 40m to the 8 times n. So B, we have more variables and more numbers, coefficients. 7, 3, and 2 are the coefficients. We could write them side by side if we don't want to just multiply it in our heads. Then we have r's and t's, so I'll cross these out as I rewrite them or reorder them. Then we have an r. Then we have an r to the 9th. And we also have t's. And finally a t to the 7th power. So we multiply all of these coefficients together. A 7 times a 3 is a 21, times 2 is a 42. Then we have two bases that are the same multiplied, and so we add their exponents and we get an r to the 10th. And then t times t to the 7th is a t to the 8th power. And this is as far as we can go in the way of simplifying this product. Okay, C, we pick out the coefficients. In front of this first component of the product, there's no number written, so it's understood that it has a coefficient of 1. The coefficient of this second factor is 2. And then we have a coefficient of 9. So we multiply the coefficients together, we get an 18. So we've used the 2 and the 9, and now we have A's and B's. So I have an A in the front and then an A in the back. We group those side by side, A times A to the 3rd. And then our B variables are B to the 3rd and a B squared, and again everything's multiplied. That's what these dots indicate. So we've taken care of the 2 and the 9. We have 18. A times the A to the 3rd would be a 1 plus 3. And B to the 3rd times B to the 2nd would be a single B to the 3 plus 2. So we get 18 times A to the 4th, B to the 5th. Okay, so we ran our course with the multiplication of two exponential expressions, and now we're going to talk about what happens when we divide two exponential expressions. So we have x to the 5th divided by x squared, just like the product in the previous section. We can expand each exponential expression. An x to the 5th in the numerator would mean that we have 1, 2, 3, 4, 5 x's multiplied in the numerator. And then an x squared means that we have an x times an x in the denominator. Well, what happens here is that a single x in the denominator cancels a single x in the numerator. In other words, x divided by x is a 1, and then the other x cancels an x on the top. Okay. And as an intermediate step, we could have just written one x over an x on the bottom, another x on top over an x on the bottom, and paired them up in top-bottom pairs, and then that would leave 3x's standing alone out to the side. Well, just as we mentioned here when we crossed those out, x divided by x, anything divided by itself is a 1, unless, of course, the exception, 0 divided by 0 is not 1. But in this case, x divided by x, we get a 1 for each of those. And then here we have the 3x's out to the side. And so in the end, we can write this as an x to the third power. So how can we do that without going through all of this expansion? In other words, how is 3 related to a 5 and a 2? Well, it's simple. 5 minus 2 equals 3. Okay. For every x on the bottom, we cancel 1 out on the top. We subtract it. So what we get is an x to the third. Okay, so for instance, we could have written this as x to the fifth over x to the third. Dropped the x on the bottom and took the 3 to the top and combined it with that exponent 5, but we would have to subtract, and that would give us x. Oh, we have a 2 on the bottom. So if we had a 2 instead, we would subtract 2 on the top, and that would give us a 3. So x to the third. The next example, the x squared is on top and the x to the fifth is on the bottom. So we expand each. X squared is x times x in the numerator, and x to the fifth is 1, 2, 3, 4, 5 x's in the denominator. If we split this up into single fractions, then we can group an x on the top and the bottom together, and then another x on the top and 1 on the bottom. But then there's no more x's on the top, and so we just simply have to write a 1 over the rest of the x's on the bottom. X divided by x gives us these 1's to the left. And then we're left with 1 over x times itself 3 times. And we end up with 1 over x to the third. So in other words, whichever exponent we move, if I drop the x squared on the top, and I'm going to combine the x's into 1x, and that x is going to be on the bottom, I'm, so to speak, moving the 2 to the bottom, and so that 2 would be subtracted. So whichever exponent you move, you subtract it when you're dealing with division. So 1 over x to the fifth minus 2 would be a 1 over x to the third power. So typically what we do is we move the smaller exponent when we're dealing with division and like bases. And so what I mean by like bases is we have an x on the top and the bottom, and there's different exponents. So this says if m, the exponent on the top, is greater than the exponent on the bottom, n, then what we're going to do is we're going to move the n. And we can't really go any further here because I don't know what m and n are, so I don't know why I put this equal sign here. What if m is smaller? Well, in that case, we move the m to the n on the bottom, the exponent on the bottom, and so we would write n minus the m. Whichever one we move, we subtract it from the other one. Okay, and it's important to note that if x happens to be 0, then these aren't true. Okay, if we have 0 over 0, then what we get is indeterminate. Okay, we could say, in other words, this quotient rule doesn't apply because this bottom one is implying that 0 divided by 0 would simply be 1 over a 0, and that's not true. These aren't equal. These aren't equal. So these quotient rules apply only when the variable cannot be 0. In that case, we get indeterminate as a result. So let's work some examples. Example 3. We look at the exponents, and on the bottom we have a 1, on the top we have a 6. The bases are the same. Both exponential expressions involve an r as the base. We don't want two r's, we only want one r, and so we'll keep the one on the top. Why do we keep the one on the top? Because it has the larger exponent 6. We move the 1 to the top and we subtract it. So r to the 6th divided by r becomes an r to the 5th power. The next expression, z to the 4 divided by z to the 6. Which one has the bigger exponent? That would be the z to the 6. So we keep that one. We replace the z to the 4th with a 1, and we subtract the 4 from the 6. We moved the 4, so it gets subtracted, and we end up with z squared. The next one, we could sort of look at this as two separate problems, an a to the 4th over a times a b squared over b. Okay, because we can't join the a's and the b's together. We just simply have to write them out separately side by side if they're multiplied. Now, in each case, the exponent on the top is larger. 4 for the a is bigger than the 1 on the bottom. 2 for the b is bigger than the 1 on the bottom. So we keep the a squared, or sorry, the a to the 4th. We keep that one where it is. Likewise, we keep the b squared, and the smaller exponent for each gets subtracted from the larger one. This prevents us from having a negative exponent. So in each case, we have minus 1, and that reduces a to the 4th to an a to the 3rd, and a b squared to a single b. And they just sit side by side. We can't combine these exponents because the variables, the bases are different. So here we have an m to the 5th over an m to the 3rd times an n over n to the 8th. So could be confusing with it cluttered together. We can separate them into separate factors according to the like bases, m's, n's. And for the m in the numerator has the larger exponent. And for the n, the one in the denominator has the larger exponent. So these are the m and n that we keep, but now we have to subtract the other one that we sort of threw away. M to the 3rd would be removed by subtracting 3 from the 5 on the top. And then the n on the top of this fraction has an exponent of 1. And so we need to subtract the 1 from the 8 on the bottom. And in the end, we get m squared and a 1 over n to the 7th. And if we multiply these two together, then we can combine them into one fraction and write it this way. And so as you get more comfortable with the exponent rules, it's really not necessary to do all of these intermediate steps. Okay, we're just trying to take it slow until you get used to the quotient rule and the product rule. Okay, when an algebraic term has a coefficient, you just divide the coefficients. Much like when the terms had coefficients and we were multiplying the terms, then we just multiplied the coefficients. So example 4, we could separate this into a fraction with the coefficients times a fraction with the x's times a fraction with the y's. Well, 10 divided by 5 is a 2. X over an x to the third. The 3 is the larger exponent versus the 1 on the top, and so we keep the x to the third on the bottom and subtract the 1. And then which y has the larger exponent? That would be the one with the 9. And so we drop the y on the bottom and subtract the 8 from the 9 on the top. We can drop the dots for multiplication, and we can write this as 3 minus 1, 2, x squared on the bottom, and then 9 minus 8, a y on the top. So the 2 sort of sitting out in front of the fraction. We could go a step further if we wanted to and write this as a 2y over x squared. Okay, with the next one, we can say that the coefficient on the bottom is a 1 because there's no number written in front of the s. It's understood to be a 1. We could group the s's into a single fraction and then the t's into a single fraction. And 3 divided by 1 is still simply just a 3. S squared divided by s is a single s. Okay, we could go ahead and write the subtraction of the exponents, but we would have the bigger one, 2, on the top, and subtract the 1 from the bottom. And then here the exponents match. So you could take it to the top or the bottom, it doesn't matter. Keep the t8 on the top and subtract the 8 from it, the 8 on the bottom. We still subtract even though they're the same. And what we get is a 3s to the 1 power, and we don't have to write the 1. And then we get a t to the 0 power. Well, what is t to the 0 power supposed to be? Well, just look back at the original expression here and think about what is actually happening. What we're doing is we're taking something and dividing it by itself. When that happens, you simply get 1. How many times will t to the 8th go into a t to the 8th? Well, that's 1 time. So anything raised to the 0 power is a 1. And 1 times a 3s is a 3s. And so all of this was reduced to 2 items, a 3 and an s. Okay, so this next page, we're going to take our product rule and quotient rule and apply them to one situation. Okay, you can see here in the workbook we're taking this first factor, 6x over 7u, and multiplying it times another factor with more variables and their own coefficients. Okay, and we have an x on the top, x on the bottom of the other fraction. So there's both rules present in this particular problem. Alright, well, we could treat this as any other multiplication of fractions problem. Okay, top times the top, bottom times the bottom. And you see that what they've done here is let's see. They've went ahead and sort of struck out some of the like variables on the top and the bottom. We have an x way over here, and then there's an x in the other fraction on the bottom. Well, they've simply struck them out and replaced them with ones. And then likewise, in this fraction by itself, there's a u on the bottom and the top, and they cancel, and they leave ones. And so then we're left with a single u in the first fraction on the bottom, and then just the coefficients. Okay, well, actually they went ahead and reduced the numbers too. A 3 will divide into 6 and 9, and we get 2 and 3. Okay, so in the end we have a 2 times a 5 on the top, a 10, and a 7 times, let's see, a 3 on the bottom, 21, and then we have that u that didn't cancel out with another one. This u canceled with that one, so there's nothing left for this one to cancel out with, so we keep the u on the bottom. Okay, what if we had divided these two fractions instead of multiply? Well, in general, say for instance we had 1/4 divided by 1/2. The standard procedure is to switch division of fractions to multiplication of fractions by writing multiplication in the place of division and flipping the second fraction. So 1/4 divided by 1/2 is equivalent to 1/4 times 2 over 1, which would give us 2/4, and that would reduce to 1/2. So likewise, if we have fractions with variables, we do the same thing. 6x over 7u, the first fraction stays the same. We kept the 1/4, but then we switch division to multiplication, and we flip the second fraction in the same step. Once we switch to multiplication, we have to flip the second fraction. Now, since we're multiplying fractions, what we can do is just combine the top together. Okay, we could write a 6x times a 9ux over a big fraction bar. These two are combined through multiplication, and then a 7u times a 5u on the bottom. Alright, we can rearrange the top as in terms of coefficient times coefficient, x times x. Okay, takes care of these x's, takes care of the 6 and the 9, and then we have a single u left. And on the bottom we could place the coefficients side by side and then we only have u's, and there's two of them, 1, 2. Okay, well, this u cancels that one out, and that's the only two that'll cancel. There's no x on the bottom that'll cancel one of these x's on the top, and so we're left with an x times x. 1 plus 1 is 2. 6 times 9 is 54. 7 times 5 is 35. And then we have a single u on the bottom. So a different result than when we multiplied the two fractions. Alright, example 5, multiplying expressions. We want to write our answer in lowest terms. Top times the top would give us a 5 times a 4. So we're done with the 5 and the 4, and we keep everything on the top that started on the top. Then we have two y's, so we write y times y, and we're just sort of grouping everything together. And then we have the t, and so we've used everything up on the top. 5 times 4 is 20. Y times y is a y squared. And now for the bottom, we can place the 8 and the 3 side by side. And then there's a t and there's a y. 8 times 3 gives us 24. And we could write these in the reverse order, so that the y is actually sitting under the y squared from the top. The t is sitting under the t. And at this point we realize if there's the same number of t's on the top and the bottom, they're just going to cancel out and leave a 1. So we could write this as 1 over 1. T's canceled. And then this 1y cancels a y on the top. We could apply the quotient rule and subtract the exponents. 2's bigger, so we keep the y squared on the top, and then the y on the bottom has an exponent of 1. If we drop that y, we have to subtract the exponent from the y on the top, so 2 minus 1. And then 20 over 24 will simplify due to the fact that 20 and 24 are both divisible by 4. So divide each one by 4, we get 5 over 6. So this is a 5y over 6. 2 minus 1 is 1. Y to the 1 can be written without the exponent 1. The next one, instead of the dot, they use the cross symbol of multiplication. We can combine these into a single fraction. Write the two coefficients side by side multiplied, and times a b and times an x. Then we'll group everything together on the bottom. 2x times 9b to the third x to the fourth would give us 2 times 9. X times the x to the fourth takes care of the x's, and then we just have a b to the third left on the end. Alright, on the top we get a 30. On the bottom we have an 18. And then for the b's, which b, top or bottom, has the larger exponent? That would be the b to the third. So we keep the b on the bottom, we drop the b on the top, which has an exponent of 1, and we subtract that exponent from the 3 on the bottom. We're not going to do anything with the x in this step, but on the bottom we have an x to the first times the x to the fourth, so this would be 1 plus 4. These two x's aren't divided, they're multiplying each other, so we add the exponents. I'll write the x term or variable first, and 4 plus 1 is 5, so this is an x to the 5th power. And then 3 minus 1 is 2, so this is a b squared. And so now what we can do is just apply the quotient rule to the x on the top and the bottom. Alright, we get a 30 over 18. X to the 5th has the larger exponent, so we keep that x on the bottom, and subtract the exponent from the top from the 5. And so we get 30 on the top by itself, 18 on the bottom, x to the 4th, and b squared. And now the only thing left to do is to simplify the numbers, and we could have done that from the beginning, but each of these are divisible by a 3. So we get, let's see, what is the largest common denominator here? Well, if I divide by 3, I get a 10 over a 6, and then I get x to the 4th and b squared, and I can divide it by 2, so I get 5, and then I get 3. And now this fraction is in lowest terms. 5 divided by 3x to the 4th b squared. Alright, example 6, we're now dividing two fractions with a bunch of variables mixed in. Alright, you might notice that there's an x on the bottom of this first fraction, and then there's an x on the top of this second fraction, and you might be tempted to cross those out. But beware, you cannot do that. In order to cross cancel from one fraction to the other, multiplication must be the operation between the two fractions. So we need to do that first. We need to switch this symbol to multiplication, and then flip the second fraction with the x on top and the 12tx on the bottom. Now if we want to, we can cross cancel. X on the bottom over here will cancel with this x on the top in the second fraction, and then the t's will cancel, we're left with a 10 on the top, a 3 times 12x on the bottom. X is our only variable now. And then the 10 and the 12 can be simplified by dividing each by 2. 10 divided by 2 is a 5. 12 divided by 2 is a 6. And now we have to multiply the 3 and the 6 on the bottom to get an 18 and an x. And so here we have it, our quotient in lowest terms. So it's very important when you divide two fractions to switch to multiplication first before you try to cross cancel. So do that in a single step. Division to multiplication. Flip the second fraction so the 9y goes on the top, b to the third on the bottom. What you can do is group all of the coefficients into one fraction if you wanted to. 5 times 9 over 3. Then you could say, well, I have a b5 on the top and a b3 on the bottom. And I'm simply putting a slash through these because I want to keep track of what I've brought to the right. We've used up the coefficients. And now for the fraction that contains the y's, we have two y's on the top, this one and that one, and then we have one y on the bottom that has a power of 3. Okay. And so things are a little organized. It's pretty clear as to what we need to do here. Things aren't all just jumbled together, which can sometimes be confusing and lead to a mistake. In terms of the coefficients, 9 is divisible by 3. It'll leave a 3 and a 1. So as far as the fraction with coefficients, we only have a 5 times 3 on the top, which is 15. Now if we deal with the fraction with the b's, we would say that the b to the 5th on the top has the larger exponent, and so we keep that one. We drop the b on the bottom. We can't just throw away the 3. We need to take it and subtract it from the 5 on the top. Okay, dropping the b on the bottom means that we put a 1, not a 0 in its place, a 1. Okay, y times y in the last fraction means that we have a y squared on the top, and then we just bring down the y to the third on the bottom. So we'll go through and change a little bit more, get it closer to the final answer. We can subtract the 5 and the 3 for the b and get a b squared. And then we can simply say on the bottom, the y to the third is bigger than the y squared, or there's more y's, exponent's bigger. And with the 2 being smaller than the 3, we just simply subtract the 2. And in the end, we simply have 15b squared over y. 3 minus 2 is 1. And we don't have to write the 1 above the y. We can just write a single y. And so here is our simplified quotient. And I call it a quotient because it came from the division of two fractions. So our third and final rule is called the power rule. And we still have two exponents. The 2 and the 5 here are both exponents. But notice that we no longer have two bases, or in this case, two x's. Okay, this is an x squared, and then we raise that to an additional power of 5. So This is the equivalent of having 5 x squareds multiplied times one another. Just like that. Okay. In the workbook, the parentheses were simply avoided and use the dots for multiplication instead. There's really no difference. Either one indicates multiplication. But we still have 1, 2, 3, 4, 5 x squareds. Okay. With all of these x's being multiplied now, what happens in the next line is that we apply the product rule. Okay. So we condense these 5 x's into a single one, and then we simply say 2 plus 2 plus 2 plus 2 plus 2 is 10. 2 plus 2, we do that 5 times, we get 10. Likewise, the addition of 1, 2, 3, 4, 5 2's can be written as 5 times 2 or 2 times 5. Okay, multiplication is just a shorthand way of writing addition. And so in the end, we get x to the 10th power. And so the power rule tells us that when we have an exponential expression with an exponent that is raised to an additional exponent, we can multiply the exponents. So as far as a general statement of the power rule, x to the m to the nth power is an x to the m times n. Alright, and so that's what we're going to do in example 7. We're going to apply the power rule. Alright, notice that we don't have two z's. We have a z to the 6, it's in parentheses, and immediately on the outside of the parentheses we have another exponent 7. This is an instant of where you want to apply the power rule and multiply the 6 times the 7 and get a z to the 42nd power. So m to the 9th raised to the 3rd power is an m to the 9 times 3. And so in C part we sort of mix it up. We have a minus 2s to the 4th inside the parentheses. And immediately on the outside of the parentheses we have the 4. So everything inside here is raised to the 4th power. We could write a negative to the 4th power, a 2 to the 4th power, and an s to the 4th to the 4th power. Well, what is a negative times itself 4 times? Well, it's just a minus, 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 minus. And if we apply the double negative rule, that simply gives us a plus from the first 2 and a plus from the second 2. An even number of negatives multiplied is a positive. Well, what about the 2 to the 4th? Well, we simply get a 16. Okay. 2 times 2 times 2 times 2. Each one of those gives us, each pair of 2's gives us a 4, and then 4 times 4, 16. And then here is just a straightforward application of the power rule. S to the 4th to an additional power of the 4 is an s to the 4th times 4. We don't need to write the pluses to indicate that 16 is positive. And here we just carry out the multiplication of the 4's, and we get an s to the 16th. And that would be as far as we can go. And it's just a coincidence that we have a coefficient 16 and an exponent 16. So in D, we can split this up according to a sign, a coefficient, and a variable. Okay. Each item inside the parentheses is raised to the second power on the outside. So this is a p to the 5th power to the 2nd power. And then we have a q to the 8th power to the 2nd power. This looks identical to the power rule up above. P to the 5th to the 2nd can be written as a p to the 5 times 2, and the q can be written as a q to the 8 times 2, and we end up with a p to the 10th power and a q to the 16th power. So really what you can do in this case is take the 2 from the outside of the parentheses and distribute it among the exponents inside. 2 times 5, 10. 2 times 8, 16. Just make sure that you apply it to the coefficients and the sign as well if there happen to be a negative. Alright, so example 8, we've got a big mess here, a bunch of different variables, coefficients, parentheses with exponents on the outside, which should tip you off that you're going to have to apply the power rule. Okay, so we'll simply deal with this first one and write this as a negative 3 squared. Okay, this 2 came from the 2 outside the parentheses. A y squared squared. This 2 came from the 2, the exponent from the y inside, and then we have an additional 2 on the outside, so 2, 2. And then z on the inside doesn't have an exponent, and so this is just a z to the 2nd power. And then we do the same thing here. Okay. And the same rule applies here as it did with the distributive property. Remember that if we had an x on the outside, and then we're adding that to a 2 times parentheses x plus 1, we couldn't just simply take this x and add it to that x. We had to distribute the 2 first to get rid of the parentheses. That's the same thing that's going on here. We can't add this x squared or this y to the 4th with this y squared before we apply the 2 and the 4 on the outside of the parentheses. And so that's what we're going to do. We've already done that with this piece. Okay. Now we're getting rid of this second set of parentheses, and we write 2 to the 4th power, this 2 to the 4th power, the x squared to the 4th power, the y to the 4th power, and the z to the 3rd to the 4th power. Okay, well, we run all the way back through the expression, and we just try to get it closer to the simplified version. We're going to apply these 2's and these 4's. Alright, so let's just double check and make sure we used everything inside the parentheses. From the first set of parentheses we had the negative 3, there it is. We had the y squared, and there it is. We had the z, and it's here. So in the second set we've used the 2 the x squared, the y to the fourth, and the z to the third, and each one has a 4 applied to it. Alright, so starting from left to right, we have negative 3 squared, which is a positive 9. We have a y squared squared, which is a y to the fourth power, 2 times 2. Apply the power rule. The z is just simply squared. You could say this is a 1 on the inside, and 1 times 2 is 2. A 2 to the fourth power would give us a 16. It's a coefficient. X squared to the fourth is a 2 times 8, or I'm sorry, a 2 times 4, 8, x to the 8th power. 4 times 4 is 16, giving us a y to the 16th power. And 3 times 4 is 12, for a z to the 12th. And so here we have z's, we have y's, and it's important to note that all of this is being multiplied together. There is no addition or subtraction in between these coefficients and variables. So we have a 9 times a 16, which is, let's see, 144. A y to the 4th times a y to the 16th. So we have two y's multiplied. That means we need to apply the product rule, multiplication, and add the 4 and the 16 to get a y to the 20th. And likewise, it's a z times another z. So we add the 2 and the 12, and we get 14. And then all we have left over is an x to the 8th power. And so here is our final result. Alright, so it can sometimes take quite a bit of work, but just try to do a little in each step. Can't do it all in one. B, before we just simply drop these parentheses, you need to pick out the 3. So we have a 3 on the outside that needs to be multiplied times the exponents on the inside along with the negative. So this would be a negative to the 3rd power, an x to the 3rd times 3, a y to the 3rd times 3, and a z squared times 3. We don't need the parentheses anymore because we've taken care of the 3 on the outside. And this set of parentheses simply has a 1 as an exponent on the outside. So if we wanted to, we could drop the parentheses because the 1 multiplying the exponents on the inside is not going to change them. It's not going to affect them. 1 times 2 is 2, and 1 times a 1 is a 1. Alright, so now we combine the x's according to the exponential rules. We combine the y's. And there's only one z, so nothing's going to happen with it past the product rule. So to carry out the product rule to the end, we say 2 times 3, and we get a z to the 6th power. A negative raised to the 3rd power. A negative to an odd power is a negative. And then here for the x's, we have a 3 times 3, which is a 9. And then this x has a 1 as an exponent. And so x times x, 9 plus 1, would give us an x to the 10th power. So we've used the x's. We've taken care of the z's, and so all we have left is the y to the third times 3. And this would just give us a 9, y to the 9th power. And then these two y's are multiplied, so we add their exponents, and we get an 11. 9 plus 2 is 11. And our last couple examples of chapter 29, we have a fraction inside parentheses with an exponent on the outside. And so what we're going to do is take this 4 and apply it to the 3, this m squared, and then the 1's on the bottom, the 2, the 6, and then the 2 coefficient. So we could drop these parentheses, but we have to apply this power of 4 to each coefficient and variable on the inside. So this is a 3 to the 4th and a 2 to the 4th on the bottom. The 4 multiplies the exponent of the m on the top. Likewise, the 4 multiplies the 6 of the m on the bottom. And then the 4 multiplies the n, the 2 of the n on the bottom, 2 times 4. And so we're really just distributing, except by the way of the exponents. On the top we have a 3 to the 4th, which is an 81. A 2 to the 4th on the bottom is a 16. 2 times 4 for the exponent of the m on the top is an 8. And then on the bottom we have an m, 6 times 4, 24 for an exponent on the bottom. And 2 times 4 gets us an 8 for the exponent of the n. And one last step to get this in the simplified form involves the m's. Okay, we have an m on the top and the bottom, and we only want one m, and we're going to keep the 1 on the bottom because it has a larger exponent. So we drop the 1 on the top and we carry the 8 down to the bottom and subtract it from the 24. We change nothing about the n. So finally we get 81 on the top, 16 on the bottom. 24 minus 8 is a 16 exponent for the m, and then the n has an exponent of 8. And this would be as far as we can go. Okay. This next one I'm going to do a bit differently. What I'll do is I'll take the fraction inside and I'll simplify it first before I apply the 4 from the outside. Because you can see on the inside we have an a on the top and bottom and a b on the top and bottom. We can apply the quotient rule before we apply the power rule. So with the a's, the a on the top has the larger exponent, so we keep the 5, and we drop the a to the third on the bottom, and we carry the 3 to the top and subtract it from the 5. And then the b on the bottom has the larger exponent, 7, And so we drop the b on the top and carry the 4 to the bottom and subtract it from the 7. And that leaves us with 1a squared on the top and a single b expression on the bottom with an exponent of 3. And now we can apply the power rule. 4 times 2 on the top and then a 4 times 3 on the bottom leaves us with an a to the 2 times 4 and a b to the 3 times 4 and a to the 8th and b to the 12th would be our final stop. Okay, that's pretty much the last example of the chapter. The last page of the chapter is simply just a summary of the rules that we've learned. This first one is the power rule. This property, where we have two x's multiplied and the exponents are added, this is the product rule. And then this last one is what we call the quotient rule, because we're dividing. And the reason why it's broken up into two is so that we avoid getting a negative exponent. Okay, so if you have any questions about it, or perhaps I worked it in a weird way, or perhaps too fast, then simply just come by my office or point it out in class, and I'll be happy to work it a different way or slower or explain it again. Thanks for watching.